The aim of this video is to try and develop a certain complex function in a series expansion. Now you could say, let's just start from a real valued function. Let's have a look at its Taylor series and then replace x by z and go home. Okay, that would be possible, but we're going to be a bit more ambitious in this video. We're also going to allow for the fact that the points around which we create our series expansion, that is actually a point where the function blows up, has a singularity, is not well defined. And that's going to be the Laurent series. So what we're going to do is we're going to develop a function around a certain point z0. But in order to lighten our notational load, we're just going to say that we're developing the function around the origin. If that's not the case, just replace z by z minus z0 in all the formulas. Okay, the function is not defined at the origin. It blows up there, so it's certainly not going to be holomorphic. So we're going to say that the function is only holomorphic inside this ring-shaped, this donut-shaped region over here. So in the inside over here, the function is nicely holomorphic, but we do exclude this part over here. And in order to make it general, we're also going to exclude points over there. Okay, so a function which is only holomorphic over here. And we need to develop that in a series expansion for a certain point z somewhere over here. How on earth are we going to do that? The trick is to make use of what we already know, and in our case that's going to be Cauchy's formula. So the question is, can we apply Cauchy's formula to a contour, for example, a contour like this? So pause the video and see if this is indeed something you could do. Well, you could do that, but the end result would be wrong, because in order to apply Cauchy's formula, what you need is a function which is holomorphic everywhere inside the contour. And in our case, the points over here, which are lying inside the red contour, are points where we've said that the function is not necessarily holomorphic. So using this particular contour is not a good idea to try and apply Cauchy's formula. So we need to be a little bit more creative and come up with a different contour. So let me redraw the stuff here. So this is the donut-shaped region where the function is nice and holomorphic. And now, rather than having a contour which we close like this, which would include the problematic points around the origin over here, what we're going to do is try and avoid the origin by closing it like this. So now with this clever extended red contour, the inside is this region over here, and the problematic region is now excluded. So for this extended contour, we can indeed apply Cauchy's formula. And you notice that this contour consists of 4 different subcontours. We have an external contour, which we're going to call C1. And then we have 2 line segments, L1 and L2. And again, just like before, we're going to take the limits of these 2 guys becoming infinitely close together, such that this contour here actually closes. C1 becomes a closed contour. And the same is true for our inner contour, which we will call C2 here. Okay, so now the goal is to apply Cauchy's formula on the red contour. Cauchy's formula requires a certain point inside the red contour. So conventionally this was called z0, but now we're going to call this z. Why? Because we want to calculate basically f of z as a series expansion. So this is why we're not going to use f of z0 here, but just f of z. Just small change in notation, nothing fundamental. And then for the integration variable, which in the original formulation of Cauchy's formula was called z, we're going to use a different term. We're going to, and let me switch to red here, the integration variable running around the red contour, we're going to call that z prime. Okay, so using these notations, split up the contour into its 4 different parts, take the limit of these things becoming infinitely close together, and apply Cauchy's formula. Pause the video and start working on this. So Cauchy's formula allows us to calculate f of z as an integral of 1 over 2 pi j of f of, in our case, f of z prime minus z d z prime. So here we just changed z naught by z and z by z prime. And if we split up this contour into its 4 different parts, then we first have a contribution from C1. Then we have a contribution from the line segment L1, from the line segment L2, and then we have a final term which is 1 over 2 pi j over the internal contour here, C2, f of z prime minus z d z prime. But again, the thing is, if we write something like this, then by convention, this means that we walk through C2 in the counterclockwise direction. But here, if you look at the way this contour is traversed, we actually need the clockwise direction in order to close our contour. This is why we have, again, a minus sign over here. And then just like before, in the limits of L1 and L2 becoming infinitely close together, it's just a continuous function where we either travel from beginning to the end or from end to the beginning. So that's a minus sign. So these two also cancel. So basically what we have is we've calculated f of z as the sum of two contour integrals. So what on earth is this going to help us calculating a series expansion? Well, the trick is to make use of a pre-existing series expansion, which is the following, which is 1 over 1 minus z is equal to the sum of m going from 0 to infinity of z to the power of m, provided that the magnitude of z is smaller than 1. So this is a straightforward generalization of a real-valued series expansion. Also here you had similar conditions, and you can actually prove, but we're not going to prove that in this case, that if you extend that to the complex plane, you get something that looks like this with a very similar convergence condition. So let's not prove this, let's just use this as an ingredient to to find a series expansion here. So one thing we should do now is try and rewrite the expressions over here in such a way that we can use this series expansion. Now the denominator here, that looks promising. It's not yet in the form of 1 minus something, but if we either divide by z or by z prime here in one of these two terms, then perhaps we can hope to write this in a form that will allow us to use this particular series expansion. So what I suggest you do now is pause the video and try to figure out whether you should divide by z or by z prime in order that all the conditions are fulfilled such that you can use this series expansion. And that will be a huge step forward in trying to find a series expansion for the whole function f of z. So pause the video and do some calculations. So it's really crucial that we respect this convergence condition over here. So we need something in this formula which has a magnitude which is smaller than 1. So let's first have a look at our outer contour C1. So if you go back to our drawing here, it's very clear that z prime on C1 is lying over here and z is inside the contour. So the magnitude of z is going to be smaller than the magnitude of z prime. So for C1, we have that the magnitude of z is smaller than the magnitude of z prime, which means that the magnitude of z over z prime is going to be smaller than 1. So if we take a look at this first term over here, and if we divide everything by z prime, we end up with something that looks like this and where we can apply the convergence condition here. So for z1, we need to divide everything by z prime. For C2, it's different because now the roles are reversed. Now z prime will be lying on the inner red contour. And now we have that the magnitude of z prime is going to be smaller than the magnitude of z. So the magnitude of z prime smaller than the magnitude of z, which now means that we should divide everything by z in order to end up with a quantity which in magnitude is smaller than 1. Okay, now that we know that, we can get to work. We can say that our function f of z is going to be 1 over 2 pi j, and then the integral of c1. So again, after taking the limits of L1 and L2 becoming infinitely close together. And let me see if I can bring them both together on the same screen. So this expression over here, I'm going to divide both numerator and denominator by z prime. So this is going to give us f of z prime divided by z prime. And then we have d z prime 1 minus z over z prime. Okay. So now that's good news, because now indeed we have 1 over 1 minus something, and that something is smaller than 1. So in the next step, we can indeed let this series expansion loose on this particular term. Good. Obviously, we also have a second term, so that's minus 1 over 2 pi j, the integral over c2. But in this case, the roles are reversed, and we need to divide everything by z in order to be able to use this formula here. So now we're going to have f of z prime over z, right? And if we divide everything by z, we end up with dz prime, and then we have z prime over z minus 1, which is almost in this particular form here. Let's just make a small cosmetic change. Let's replace this by 1 minus z prime over z, and then let's quickly compensate for that by changing this into a plus sign. So now we're really in good shape. We can directly apply this particular formula over here. So let's do that. Let's now write that our f of z is equal to 1 over 2 pi j, and then we have the integral over c1 of f of z prime over z prime. And then now we have our series expansion. So we have 1 over 1 minus something, and the something is smaller than 1. So this teaches us that we can write this as a sum of m going from 0 to infinity. That's something to the power of m, and the something is z over z prime to the power of m, the z prime. Okay, let's now do the same thing for the second term. So this is going to be 1 over 2 pi j integral over c2 f of z prime over z. And now we have the summation of all possible powers of z prime over z. So now we have the sum over, let's call this n going from 0 to infinity, z prime over z to the power of n d z prime. And you might not immediately realize this, but what we actually have at this stage is our famous series expansion, because we have all sorts of powers of z here. And remember, we have these integrals, but the integrals, in terms of integration variable, we have z prime. So z is actually a constant when it comes to the integration. So we can safely bring out the power of z outside of all of these integrals. So we're basically almost there. What I suggest you do now is pause the video and try to clean this up a little bit so that it becomes very clear that this is a series expansion including both positive powers of z and also negative powers of z. And it's obviously the presence of these negative powers of z which allows us to express the fact that the function is singular at the origin, where we expand the function. So pause the video and do some cleaning up work. Okay, Obviously, since we have well-behaved functions here, we can exchange the order of summation and integral. And again, since z does not depend on the integration variable, we can just bring this outside. So we have 1 over 2 pi j, and then we have a sum of z to the power of m, a sum where m goes from 0 to infinity. And then what we're left with is basically the integral over the contour C1, okay? And so what's inside, basically, so we have f of z prime. Okay, we have f of z prime. And then taking a look at z prime, so we have z prime to the power of m here, and then we have another one over there. So we have basically z prime to the power of m plus 1 over here. So this is the result of rearranging this first expression over here. And remember, this thing looks scary, but it's basically just a number, right? So it's you can write this as am. So what we have here is a series expansion of powers of z, positive powers of z, multiplied by a certain coefficient, and the coefficient can be calculated by evaluating this slightly scary looking contour integral. But we're not yet done. We also have other contributions from that second term, so which is going to be 1 over 2 pi j, and then if we bring out the negative powers, so we have then n from 0 to infinity. So now what do we have in terms of negative powers of z? We have basically z to the power of minus n minus 1. I just turn this, if I get rid of the denominator here, we have z to the power of minus n minus 1. And then we have an integral over our inner contour C2. So what do we have left? We have f of z prime, obviously. So what do we have in terms of other things that depend on z prime? We have z prime to the power of n d z prime. Okay, so that's again the same story. We have, in this case, negative powers of z, and this thing is just a scary component, but it's just a constant in the end. So we have a similar situation. Now what we can do is slightly rearrange this a little bit such that it looks a lot more like this thing over here, and that it becomes really clear that we just have all the positive powers, all the negative powers, and also the power of 0 here. What we're going to do is make a small change of variables here, such that basically we have a new summation index n prime, which is going to be n plus 1. Now in this case, so if I don't copy the first term again, but just focus on the second term, we have 1 over 2 pi j, and then we have the sum of n prime going from 1 to infinity in this case. Okay, so now we have, previously we had z to the power of minus n minus 1. So minus n minus 1, that basically just means minus n prime. So we have z to the power of minus n prime, which makes it look a lot more like z to the power of m here. So that's a lot more symmetric. Let's see if the trend continues. And now we have the integral of the contour C2. We have f of z prime. And then we have z prime to the power of n. Okay. Now, if we want to bring this into a form that looks more like what we have over here, we basically need to bring this to the denominator. So in the denominator, that becomes z prime to the power of minus n. So z prime to the power of minus n. So minus n is just going to be minus n prime plus 1 if we look at this thing. And again, if we write it like this, that basically shows you that it's exactly the same structure as the equation we have over here. The only thing we need to do is replace these minus n primes by plus, basically, so just flipping the sign here. so that here now we sum over negative powers of z. But the important part is that the end result can be written in the following form as a sum over both negative and positive powers of z, so z to the power of m, times a certain coefficient, which can be calculated using the contour integrals. So these are the Laurent series expressions that we were after. And again, it's a generalization when you compare it to a Taylor or Maclaurin series, because now we also have these negative powers of z. And the reason why we have these negative powers of z is such that we can also accommodate for the fact that f of z might have a singularity at the origin. So this is the story of the Laurent series.